Welcome to the second session of MEDEAS Economy Module topic. Today, we will learn how the MEDEAS Economy Module works. After having set our theoretical framework in the previous session, we need to translate it into the model's structure. So we have built an economic module which allows us to represent the final energy demand as accurately as possible. So in this session, the general framework will be described, and the structure and module and some examples will be shown. But first, just a quick reminder on the role played by the economy module in MEDEAS. Basically, the economy module triggers energy demand, which makes the energy module extract primary energy sources from the environment and transform them into the final energy that is being demanded by final users within the economic system. As can be seen in this overview chart, the economic activity is, either directly or through the energy module, what brings about energy and material carriers, as well as pollution impacts. However, because the economy cannot trespass biophysical boundaries, the relationship between energy and economy is two-way. Therefore, it is important to set a realistic energy economy nexus. This link has been traditionally pictured as a linear one-way relationship. Regardless of the causality direction here, what the data are telling us is that it takes energy to produce economic output. So we can all agree on this direct relationship. However, what is often missing in models is a feedback so that if the energy inflows to the economy are lower than required to meet a certain growth rate, then the result will be a GDP slowdown. As we have a stock of non-renewable energy sources and renewable energy source potentials, which will be explained in the next module, and the energy flows to the economy depend on them, as well as infrastructures and their productive capacity, the economy must dynamically adapt to the net energy availability in every simulation period, and therefore to biophysical boundaries. With a more in-depth insight, the economy module works according to this overview. First of all, GDP per capita and population scenarios lead to an exogenous demand shock, giving our sectoral demand function the expected labor compensation and profits for the current period. This function estimates the final demand of products and services made by 5 institutional sectors from 35 different industries. Then, we calculate the production required to satisfy this sectoral final demand through an input-output analysis of both direct and indirect effects. After that, by using energy coefficients, which are the energy intensities, energy demand by the 35 sectors and 5 final energy sources are obtained. In parallel, the energy module estimates the final energy supply according to its structure, which has been described in the previous module. If the final energy available by any source is lower than the final energy demand, then a scarcity coefficient is calculated, and not all the production firstly estimated can actually be produced to satisfy demand. This begins a backwards analysis, whereby we obtain the feasible production and demand, which at the world level is equal to GDP. So energy demand would be a function of energy intensities, the economic structure being represented by Leontief matrix, and final economic demand, which in turn, as mentioned before, is a function of income and its sectoral features. The 5 institutional sectors that demand goods and services from the 35 economy branches are households, non-profit organizations serving households, which has been integrated in just one institutional sector, corporations making gross fixed capital formation, or most commonly known as investment, governments, and the residual changes in inventories. Because MEDEAS world takes the global economy as one country with no external sector, exports are not included. Nevertheless, rest of the world is one more institutional sector in MEDEAS Europe and MEDEAS country, which enables including exports. Although panel data regressions were run to estimate final demand functions for each institutional sector, except government expenditure and changes in inventories, which remain a constant proportion of the final demand, coefficients are open for the user to be re-estimated. The standard structure of the final demand relies basically on the expected and the previous year's income. Hence, final demand is path-dependent and expectation sensitive. Furthermore, the input-output analysis is a methodological framework whose main advantage is that it allows both direct and indirect production carriers of the final demand to be estimated. Let me illustrate this with a quick and simple example. Imagine an economy with three sectors: agriculture and raw materials, industry and services. Whenever a household or a corporation or the government demands services from the service sector, it's not only this sector which produces a monetary output. They will need products manufactured from the industry sector, and then in turn, it will require raw materials to produce them. As a consequence, if new services are demanded, it will also make the other sectors produce output. Input-output analysis is also very suitable for hybrid economy environment assessments. Fortunately, input-output databases have been improving quite quick lately. So we can use the final energy required by each sector to produce 1 unit of output, namely the energy intensity of 5 final energy sources. Thanks to the hybrid input-output analysis, we will be able to calculate direct and indirect energy carriers of the final demand, broken down by final energy sources. After a few transformations needed to operate the input-output analysis, we can also track down which sectors are more energy intensive and the ones that rely the most on dirty non-renewable energy sources. Let's have a look, for example, at the energy sensitivity of the world economy for the last year available in our database. Basically, it measures the final energy carriers in exajoules triggered by an additional $1 million of economic output. For many people, the reliance of Sector 1, which is agriculture, forestry, and fishing, on liquids is striking. We can also see the high dependence of mining sectors and refineries on gases, liquids, and solids, mainly natural gas, oil, and coal. On the other hand, we can see how other sectors such as education, health, or other community services are less energy sensitive. This kind of information is very useful for policymakers, but also for the modeler to make decisions in MEDEAS. The demand for non-renewable energies can be lower in scenarios where the energy intensity drops sharply. An energy mix shift is operated or a deep economic structure change also occurs. For the sake of simplicity, in this course, we will keep economic structure static. But industrial policy favoring less energy-intensive sectors to the detriment of the more energy-intensive ones is an important policy for energy transition. Now we are prepared to have a look at some model examples, which can illustrate how the energy economy feedback works. For this purpose, we have run the model with and without the feedback. Let's take a particular sector, say Sector 15 of transport equipment. Here we can see that the final demand of this sector's product or services if we disregard energy availability. As a result, according to the economic structure, this sector needs to produce a certain amount of output, which in turn encompasses this demand of final energy sources. We can see the electricity demand share rising as electrification goes ahead in the model. If no feedback is considered, production is satisfied and the economy-wide GDP can keep on growing. But if we include the energy economy feedback, the model will tell us a different story. Now, if energy inflows to the economy are lower than required to grow at the exogenous rate that we have used, it will just grow at a feasible growth rate given the net available energy supply for every period. Let's take the same sector. We see that the supply of liquids doesn't systematically match demand for this scenario. As a consequence, the energy actually consumed is lower than expected, and therefore output is reduced from its expected trend. As a result, GDP suffers a slowdown in the next period and the following years. Meanwhile, in the energy module, different scenarios of energy transition are being unfolded. Technology is evolving, energy efficiency is improving at different rates, and energy return on investment is being pushed in different directions according to the type of energy transition chosen. We will go into this in greater depth in the next module. Finally, we are able to summarize the main conclusions of this topic as follows. One, the economic system is a subsystem embedded in a larger system, the biosphere, and therefore sustainability should be analyzed as a scale issue, the size of the economic system within the biosphere. MEDEAS Economy Module is a simulation, demand-led, and sectorial disaggregated model. The energy economy feedback plays a key role to understand the limits and challenges which energy scarcity poses to economic growth. And finally, economic demand is the main driver of MEDEAS because it activates every other module through final energy demand, direct or indirectly. This has been the final of the MEDEAS Economy Module topic. Now, you can go deeper on MEDEAS model and learn how the energy demanded by the economy is generated in the energy module, which will be explained in topic 3.